So, this is the second lecture for Computer Science 305, CSCI 305, programming languages. And today we're going to be talking about the history of programming languages. So, there's a whole bunch of stuff going on. Programming languages history is far larger than anything that we're going to talk about today, but we're just going to kind of give you a short glimpse into some of the most important parts of what's going on. And so the first thing that we want to talk about is the story of Babylon, right? Way back in the day, 1790 BC, there was, they were using cuneiform. Cuneiform is essentially a way of writing that was based on, it was a variety of different, they were sort of triangular-looking marks that, when put together, formed language. The interesting thing about this is they have a significant number of these clay tablets that they were using that were put together. But the beautiful thing about this is they actually were writing algorithms as a part of what they were doing. And these algorithms could describe contracts, records, math, all these different really interesting things. But they were using base 10 digits. Actually, it was base 60 digits that using that, they could actually describe more interesting mathematical notations, which we see here. But it was one of the most important things was they actually had a written language to describe computational procedures, and that's what that we have here. And I really like this. This was featured by and translated by Donald Knuth, who wrote the Art of Computer Programming books. But so you have a cistern, the length equals the height, a certain volume dirt has been excavated, the cross-sectional area plus the volume comes to 1, 10, which we saw earlier was in base 60, the length is 30, what is the width? You should multiply the length by 30 and then it continues. So basically they were describing algorithms for calculating things. And that's this goes back, way back. So that leads us into what is this programming language? Well, the programming language had no variables, but instead had numbers serving as running example of the procedure being described, and then this is the procedure, right? Programming was this type of programming was among the earliest uses to which written language was put, and so that we've been doing this for well before we had any type of automated device such as the computer that allowed us to do this. We've just been doing this as humans, and so. That brings us to the next story, right? Muhammad al-Khwarizmi. Now, this is in Baghdad, right, which is near the ancient city of Babylon, found back in 762. Baghdad at the time was considered to be one of the greatest centers of scholarship, art, and poetry ever, right? And this gets into prior to the first and second scientific revolutions, but. Al-Khwarizmi was the court mathematician, and he wrote 2 little books. I'm not going to be able to pronounce that, but it was basically the concept that led to algebra, right? Translated into Latin, this book ended up becoming the mathematics text in Europe for approximately 800 years. That's an extremely long amount of time for a book to be influencing the mathematical world, right? Then he wrote a second book, which was on algorithms. And unfortunately, the original was lost, but there was a Latin translation, Algorithmi de Numero Indorum. And basically, this book composed of algorithms for computing with Hindu numerals, which is the basis of the base 10 system that we use right now, which is the base 10 positional system with 0, right? That's what we use today. And this was a new technology, right? Data structures and algorithms. And it had a very strong influence on medieval European mathematics, right? So there were, along with what was going on here in both Babylon and Baghdad. Euclid was in Greece was also working on some interesting things back in 300 BC, which includes how do we find the greatest common divisor. I'm sure we have all learned Euclid's algorithm when we took discrete mathematics, right? But there was also Alexander de Villiers, who in 1220 AD, wrote a book on algorithms in Latin verse. None of these are actual programming languages, but natural language plus mathematics, right? So, but it is still a method by which we can describe algorithms, and that's really what programming and programming languages do. That leads us into Augusta Ada, the Countess of Lovelace, and a very interesting story. So Augusta Ada was the daughter of George Gordon, Lord Byron. Okay, in the early 1800s in England, women were generally denied education, as was common during that time, especially in math and science. So in order to get around this, Ada was studied with math with a private tutor, and was married at 19 and became Lady Lovelace, and she had 3 children. Well, the interesting thing was, right about the same time, there was a man named Charles Babbage. He's an English mathematician, and he was working on developing mechanical computers, right? And he created, or designed, let's put it like that, invented what he called the difference engine. Now they started construction. Wasn't complete. The reason it wasn't actually complete, I believe, was that it was based on a significant number of gears and timings, and I would suggest going out on YouTube and looking up the difference engine and the analytical engine. They actually have working models of them, or actually working constructions of them, but they you can see them actually operate. Well, the problem was the actual gearing they needed to do was need to be precisely created, and at the time they did not have the ability to create the gears with the precision necessary. Anyway, and then he actually developed a second one, which is called the analytical engine, but was never built. So given that, the analytical engine, right, had a bunch of different things going on. So it had a processing unit, which he called the mill. It had memory, which he called the store. And then it had programmable punch cards. And this is the interesting concept. This is where punch cards came from. And so with this, it also had the capability for iteration, conditional branching, or if-then statement type experience, as well as pipelining, and then and then it had the capability to export to input-output devices, right? So there was a sketch of the analytical engine in a paper by Luigi Menabrea, published in 1843. And then this was translated with explanatory notes by AAL, which is Augusta Ada of Lovelace. And so the algorithms, then there were algorithms in a real programming language, right? The machine language of punch cards for the analytical engine. And the interesting thing is, so this is what she had to say about this. The bounds of arithmetic were, however, outstepped the moment the idea of applying the punch card, the cards had occurred, and the analytical engine does not occupy common ground with mere calculating machines. In enabling mechanisms to combine together general symbols in successions of unlimited variety and extent, a uniting link is established between the operations of matter and the abstract mental processes of the most abstract branch of mathematical science. So, given that, right, and I want to stop here. Ada Lovelace became what essentially is the first programmer, right? She developed these algorithms for this language, for these punch cards, and then there was a whole thing where she and Charles Babbage were lovers, but I'm going to leave that to history, and you can go read about that in your spare time. So that's the prehistory of programming languages. This is before we had actual languages for programming, right? We had concepts, we had ideas of algorithms, but we didn't have an actual language to describe programming yet. And that brings us to this next story. So this is Comrade Zeus. Comrade Zeus was quite an interesting man. He was built. In his parents' living room in Berlin in 1936. This gentleman developed a mechanical computer. Call it the Z1. Actually, I believe that would be Z1. And it was based on metal strips and pins, which is completely in contrast to how Babbage was building his mechanical, which is based on his mechanical computing engines, which were based on wheel work and a large number of gears that were working together. It was also programmable using punch tapes, but it had what it brought in was the capability to handle floating point numbers with an explicit exponent, right? He further went on to develop three more different mechanical computers, including Z2, which experimented with relays for the arithmetic and logic unit, as well as Z3, which was all relay technology, the first electronic programmable digital computer. No longer is it mechanical. This is electronic. And then he went to Z4, which he envisioned as a potential commercial system. Now, here's the problem, right? At the same time, now Comrade Zeus is a Jew and living in Berlin, in the 1940s and 30s. This is a dangerous time for him. And so in 1945, he fled Berlin with his wife in the Z4, but the rest of these things were destroyed during the war. So in 45 and 46, Zeus completed the design of a programming language, the Planck-Concol. And what this thing does is it was a full programming language, had assignments, expression subscripts, constructed types, right? He based them on primitive bit, so you can build these types from the primitives into actual constructions like integers, reals, arrays, etc. The beautiful part about this was he also had a conditional execution, right? So if-then statements, loops, and subroutines. And finally had assertions, the capability to test if things are working as properly. And then with this language, he developed a number of example programs, including sorting, graphs, numeric algorithms, syntax analysis, chess. All these things we expect to see with a fully fledged, developed programming language. And so this is kind of what it looked like. So you had the statement line, the main line, and then you had three things underneath it, which describe what was going on. You had V, the variable number, right? And then K, the subscript, if any. And then you had comments, optional comments that describe the types of these different variables. So if we want to say VO sub Z1 plus or equals 1, this is essentially what we get. Now, the problem with this was not the language, but because it seems, it's quite influential, right? It's the first programming language we've ever developed. Unfortunately, no one knew about it. This is the problem, right? It's not published until 1972. Well, a lot of stuff happened between 46 and 72, and so especially in the computing world. So that was the time when Turing was working with the code breakers at Bletchley Park, and then all those people went on to develop actual computers, and we had the ENIAC. A lot of stuff was happening while he was not publishing this language. So, unfortunately, it never was implemented, mainly because there was nothing to implement it for at the time when he developed it. And so, luckily, though, a significant number of his ideas had been reinvented by others. And so that leads us to the next story, right? The labor of programming, right? Programming essentially has always been difficult. Back when we first started this whole thing, the early days, large-scale digital computers, and we're not talking about necessarily, the women programming the ENIAC by moving giant jumper cables. We're more referring to the next phase, which was very tedious, right? Now we're thinking about this. You had to know the codes associated with individual operations you want to perform, and then where in memory the actual address is for what you were trying to operate on. So it was quite disturbing, and this is what Dr. Grace Hopper had to say about this. Rear Admiral Hopper had to say about this. Is that back in the old days of programming, basically, they programmed in octal. Like, they wrote numbers to describe programs. The problem was even then, a little later, right? The next thing that people said was, "Oh, the only way to do it is use assembly." And so the interesting thing was, she's sitting here saying that I have a copy of the manual for the Mark I, which was the system that they were using, and she says that I think most people would be totally flabbergasted if you look at this. You're faced with programming a computer using the Mark I manual, because all it really was a listing of the codes for the different operations you're trying to do. So the octal codes for what you were trying to do. And then you're on your own, right? And now we have to take this into context. Who was Grace Hopper? Well, Grace Hopper developed the first compiler, to solve problems like this. And even then, she was saying that, the concept of the word programming was not a thing at this time, right? They called themselves coders. Why? Because they were just writing code. They were writing codes, literally, to describe what they were doing. The word programmer hadn't even come over from England, as the case was, yet. So now, this led us to this wish list, right? I mean, coders, this floating point numbers were like unheard of. These are things that coders, if they were going to do this, they had to keep track of where the exponent was, right? Where the, manually. That's insane today. They had relative addressing, right? So you had to know where they had notebooks of subroutines, but the codes had to be adjusted. So every time, so you had a listing of the subroutine, like on paper. You wrote it on paper so you could remember it. But every time you wanted to use that, you had to adjust the actual absolute address by hand. So this is the address in memory, so the location in memory where things are going to be stored for when you're going to use this. They also wanted to have array subscripting. And furthermore, they wanted to do something other than having to remember opcodes that were written in octal, right? This is how it was back in the day. We didn't have the things that we have now. So that led us to the next level, right? So instead of having to use octal, we moved to assembler, right? Assembler now gave us names, like add instead of 075, right? And so you had names for the different opcodes. So that's what assembly got us to. And then we use assemblers to translate that into actual essentially binary, right? We also add programming tools, right? Shortcode, A0, A1, A2, which was built by Grace Hopper, and which was essentially a collection of macro libraries. Speed coding, which was developed by John Backus in '54. This is about the time in the late '40s, early '50s, when we started realizing that saving programmer time was probably one of the most important things we could do in order to improve the concept of software development or programming in general. But we realized that essentially there was a deeper problem here, right? Assembler was better than octal, but it still wasn't great. And so what we wanted was something that was a little more easier to write, easier to read, and we could store, right? And this led us to John Backus was working at IBM, and that's when he and his team sat down. They developed a new language. They called it Fortran, right? It was the IBM Mathematical Formula Translating System. Okay, this is '54. Now, the concept here was to build this high-level language which allowed them to do mathematical operations, scientific operations, such that you could get rid of some coding errors, right? We have compilers, we have things like that would allow us to not have to deal with the coding part, where coding here represents writing things in octal or hexadecimal at the machine level. And then we could also have the capability of shifting from having to know exact addresses to having relative addresses. And so that gave us this concept, and we want tools to help us. And so part of that, second thing was we wanted to improve the efficiency of writing code, right? And to make more efficient code itself. The whole concept of was to develop a tool, the compiler, that could make efficient code from this high-level language that is comparable to handwritten code. Back then, you'd find this guy, sitting in his cubbyhole in a dark room where he felt that it was much better. The code that he wrote by hand, the assembler that he wrote by hand, was far better than whatever this magic compiler device could do. I've met those guys. They were kind of interesting to talk to. But there was a problem, right? It was closely tied to the IBM 704 architecture. It's not necessarily a problem back then. It would be a problem now. But the interesting thing was, they thought, oh well, this is this has never been done. It'll only take 6 months. It ended up taking them 2 years. But regardless, it was built. And so now the first Fortran, right, had no separate compilation, right? So that meant that you could not compile separate files. You had to compile all files all at once, right, to make the program. All the parts had to be right there at the time you needed to do this. Well, if you had more than a few hundred lines, right, that became quite impractical. And the reason for that is because when you're trying to do compilation, the IBM 704 system had a mean time to failure for a process, right? And if you had large programs, it actually would reach or step over that boundary, and then it would fail. Because so what Fortran 2 did was it add that capability, so you could have separate compilation. And then finally, there was this later Fortran systems evolved with separate platform independence. You don't have to worry about the pause statement. We're not going to concern ourselves with what that means, but the interesting thing was a significant number of the things that we came up with Fortran were going to be used by almost all other languages after it. And that's what CAR Horror is trying to say here in 1982. It's like, I don't know what language of the year 2000 will be, but I do know it will be called Fortran, right? And what he's really saying is it will extend from Fortran, and no one expects Fortran to be, should not have expected Fortran to be the language of 2000, but interestingly, it is still used today. But Fortran's influence, like I was just saying, is that a significant number of languages follow. But everyone learned from Fortran. Fortran has influence, and even if you don't know you learned from Fortran, you did. And so, and that's because Fortran, these guys built scanners, parsers, the concept of register allocation, code generation, optimization, all came, and how we do that, and a lot of the techniques all came from the Fortran project, or at least the current ones have been influenced by what came from the Fortran project. Now, John Backus is an interesting guy, and we'll talk about him even later, but he had a significant number of contributions. He was the creator of Fortran. He worked on Algol 58 and 60, which we'll talk about in a bit here. The Backus-Naur BNF, the Backus-Naur form for which describes languages and grammars thereof, he came up with as a part of the Algol project, if I recall. And then FP, which is a purely functional language. So there's this really nice quote here, and what he's saying is that it's was a benefit to, and also a detriment, that all of our languages were sort of based on the concept of the von Neumann architecture, right? You have stored memory, a processor, and the capability to move information to and from that. Unfortunately, though, his argument was that essentially it's going to probably limit our way of thinking, and make it difficult to understand and adopt new ways of programming. And I would say that partially he's true about that, but we're not going to get into an argument from or away from that. It's just that it's interesting that he said that back in '78. That leads us to the next story, right? This is the story of Lisp. So, an AI conference in Dartmouth in 1956, Makarsky, Minsky, Newell, and Simon were all together, and Newell, Shaw, and Simon demonstrated this program they had written called the Logic Theorist. It was a reasoning program written in the IPL, the Information Processing Language, and the interesting thing about IPL was that it supported linked lists. So linked lists, we all know what that is, right? But this whole concept caught McCarthy's attention, because he wanted a language. McCarthy wrote some brilliant papers on artificial intelligence. I've read several of them, but he was talking about how he wanted a language for AI projects, but he didn't want to use IPL, right? He thought it was too low level, too machine specific. He wanted something that was able to expand beyond the initial environment, and was we'll say a little more high level. Similar to how Fortran was high level versus assembler. So there was an IBM group consulting McCarthy, and they developed another language which is based on Fortran. It's called the Fortran List Processing Language. And so McCarthy had his own wish list. He developed while he was writing a whole bunch of different AI programs, including chess and differential calculus and all these different things. And what he said was he wanted something that had the ability to do conditional expressions, the ability to have recursion, as well as higher order functions like ML's map, which you'll learn about when we talk about ML. But he also wanted garbage collection. The ability to clean up memory as needed while the code is actually running. And looking at what he had for his wish list, he saw that the FLPL wasn't the answer for what they were trying to do. And so what he did was he developed Lisp. And basically how this kind of came about is, if you look at this, Lisp has this really interesting structure. So what this it's a list representation of an abstract syntax tree. Don't worry what that is. We'll talk about that in the next lecture. But basically what's going on here is you have to think about this as the way what we're saying this. So this statement says we're going to add, that's what plus stands for, A plus the contents, the evaluation of star BC. And so what star BC is saying, we're going to multiply B times C. So it's a postfix as opposed to what we're typically used to seeing in infix. So in an infix notation, if you want to say A plus B, we would say literally A, the plus sign, B. In Lisp, we would put all in parentheses plus A, B, right? So you can also think about this as a list. And the one that we're seeing here is a list of lists. And the components of this list are the plus, which is an operator, A, and then the inner list, which is composed of the operator star, and then the symbol B and C. And so what's going on is we can break that down to a parse tree, or an abstract syntax tree. Well, the interesting thing about this was, and the initial thing was they were trying to do this in a Fortran-like notation, but McCarthy, he was trying to figure this all out, and he realized that he could write this really simple evaluator, or an interpreter, by creating a function called eval. And all eval does is it interprets Lisp and then executes it. And that ended up becoming the first Lisp interpreter. And how it works is it uses this list-like representation of an abstract syntax tree. So the interesting thing about Lisp, which stands for list processing, is that everything's a list. And so, as it says here, to avoid the syntax issues, McCarthy continued just using the list AST form, both for eval input and eval itself, right? So now we just have this hand translate. He originally translated the very first version into assembly, and then that became the first implementation of Lisp. Now the interesting thing was the group that was building Lisp never really gave up on this idea of having this Fortran-like syntax, but they never got around to it. And some people have later tried to make a compilation, tried to compile Lisp from Fortran or Algol, but none of that ever caught on. Lisp is still around today. You can get it for every major operating system. It's a really interesting thing. I suggest anyone who's interested go learn about. So there's an interesting thing. There are lots of different advantages of having programs and data use the same syntax, right? Because the data is the symbols A and B and C, as we saw in the previous example. But not only, so that's the data uses the same, because you can form that as a list, but the actual operations also use the same syntax. And we'll see this type of thing when we get to Prolog. But then Lisp started evolving. So now McCarthy made a very good case for this as a way of handling artificial intelligence. And so that really caught on. And there were all these different things, logic versus symbol, AI stuff. But up until the A's, every AI research group in the world, essentially, has its own dialect of Lisp. And then in the 70s, I think it was McCarthy, but I know it was the MIT group, started building Lisp machines, so computer systems specifically designed to process Lisp in a very efficient, fast way. And then each one of these had their own special dialect. Finally, though, at this exact point in time, there's what we call Common Lisp. Common Lisp is where we took all these different ones, we distilled down into a standardization, and now we have a Lisp itself is quite an impressive, full-fledged language and has an API to handle pretty much any type of thing you want. Now there's a subset of Lisp called Scheme, which was developed, I think, also at MIT, which is smaller and simpler dialect. It's a little easier to learn and use than standard Lisp or Common Lisp. But Lisp had, you could basically call this the second oldest general-purpose programming language, and it had an extreme influence on today's stuff. A lot of the ideas, like conditional expressions, recursion, were adopted by Algol, and later by almost every imperative language, including Java, Python, Ruby, C#, C++, function-oriented approach, which influenced almost every major functional language that exists today, including ML, which we'll learn about. And then finally, they developed garbage collection, right? That's the basis for what's used in Java, C#, a significant number of other languages, Ruby, for example. So this takes us to the next step in the road, which is Algol. So back in 57, languages were proliferating, right? Every major computer manufacturer was developing their own platform-specific languages, like IBM's Fortran, Europe. There were a whole bunch of languages being designed by different research groups, including Planck-Cole and others. So these guys got together and they said, we need to stop this. It's getting too hard to be a programmer because every time you can shift from one place to one company to another, or from one piece of hardware to the next, you have to know a brand new language. So we need to have one universal international machine independent language for expressing scientific algorithms. Well, the problem here, the problem is they got together as this giant international committee, right? You get people from everywhere, they want to get together, and they were going to come up with a design. So there's this well-known, what we'll call anti-pattern for doing things in computing technology. It's called design by committee. Usually does not work. But that led to the Algols, right? So eventually, with this large international committee, they developed 3 different languages, Algol 58, 60, and 68. Every time they went to go develop these things, there's a larger and larger international committee. It did not really work out well, but there was some good news. Virtually all languages after 1958, right? Algol never caught on, but Algol pioneered a lot of great things. For example, compound statements, where it doesn't have to be begin and end, but it can be, for example, in Java, we have curly braces that create block statements, right? We can have compound statements, free format lexical structure, right? Where you don't have to have a specific structure to your code. For example, think in Java, we don't care about white space and the way stuff is structured as long as it's within the right grouping. This is, like I said earlier, the BNF, the Bacchus-Naur form for describing syntax came from the Algol project, and we'll talk about that in the next lecture. Local variables with block scope came from this. Stack typing, nested if-then-elses, call by value, recursive subroutines and conditional expressions, dynamic arrays, first-class procedures, user-defined operators. All this stuff came from Algol. So, there was this concept of phrase-level control, right? So, back in the old days, early languages used to have this label-based control, right? You create a label, and you call it 27, and you said, go to 27 if A minus B is 5, 6, or 7, right? So Algol languages had good phrase control, like using if and while. as you know from Java. Then you also have the switch for and until. So what this allows us to do is control the state of execution, right, or the flow of execution. Well, back in the old days, you had these go-tos, and that ended up had a significant problem, right? Go-tos lead to what they call spaghetti code. And so you have all these different go-tos, you have no idea what's going on, you have to remember what was up there at that label that you're going to, and so it caused all sorts of problems. And so Edgar Dijkstra wrote a famous letter from back in '68, and I suggest anyone go read it. Go-to statement considered harmful. I've read this, it's beautiful, and he was talking not about just go-to in general, but he was talking about go-to in general, not specific go-tos, like if, while, switch, for, and until all use a go-to under the scenes, but it's very controlled. Even in Java, although we'll state to the contrary in a minute here, but even in Java, we still use go-tos, or you can, within the context of a labeled while statement. So you can have labeled statements in Java, and you can use go-to, but it's frowned upon, and it's only allowed within certain small context. That being said, Dijkstra's comments on the go-to influenced a significant number of people to the point to where you almost never see it. I know very few people who have ever actually used the go-to unless you programmed it in BASIC or something like that. You should not use go-to unless you know what you're doing. That's what Dijkstra was trying to say. This then brings us to structured programming. This is where we started shifting from, instead of using labels, we used phrase level control, right? If, switch, while, all these different things. That led us to structured programming. But it was basically a revolution, right? To the point where so it says some languages like Java allows go-tos, and go-to is a keyword in Java. So that needs to be stated. But for the most part, it's eliminated. C++ still has it. Ruby, I don't think, has it. Common language, like I don't think you can do it in C#, but it doesn't really matter. It's rare to see it, and most people don't use it. It's, for most part, you realize that if you have to use a go-to, there's something wrong with your code, and that's probably true. And all this whole revolution against go-to was pretty much triggered by the design of algo languages. Then remember we talked about orthogonality, right? Algol was pretty much where orthogonality came from, right? We wanted this free-form lexical structure. We didn't want arbitrary limits like in the names or dimensions of arrays, and we also wanted to have, a meaningful small set of primitive concepts where all the combinations were legal. We didn't want to have special forbidden combinations. Remember, that's what we were talking about earlier, and that's the key concept with orthogonality. The interesting thing about this is you have passing parameter, you have integers, arrays, and procedures, storing a variable, storing an array, returning from procedure. Each combination not permitted is a special case that must be remembered by the programmer. By Algol 60, all combinations above became legal. Just a sample of its orthogonality. Few modern languages take this principle as far as Algol. So you still can't pass just it's not that you can do anything, but you can actually, for example, in Java, you cannot return a procedure from a procedure. In C++ and C, you can, if you return a pointer to the function. So just bearing that in mind, not everything is permitted. But the bad news was, like I said, Algol languages are not as widely used as had hoped, right? Algol 58 has been extended into a language called Jovial, and Algol 60 was used for publication of algorithms, but was never actually implemented. Was never actually used very widely outside the U.S. There were several reasons, but we don't actually know exactly why it was never used, but they did neglect I.O. I remember talking to a previous professor here who stated that one of the problems with the Algol was it was extremely difficult to learn, but they had this is really beautiful. He said is extremely beautiful to look at, and they had this really great manual for it. but it was just so complicated that there's no way it was going to catch on. There was a few mistakes, by name parameters was an issue, but the more important thing was, even I would say, even like today, there was no corporate sponsor for the language, right? Think about all the languages that use. Oracle sponsors Java. Before them, it was Sun Microsystems. C# is the flagship of the .NET platform by Microsoft, right? Their version of JavaScript is TypeScript. That they have really expanded out there. Google has its languages, Go and Dart, which is their version of JavaScript. They have JavaScript itself was promulgated by Netscape back in the day, but was also developed in conjunction with Sun Microsystems. Delphi is a type of Pascal that was put out by Borland for a long time. The Borland C++ was huge. So in that arena, there's all these different languages that have had so much corporate sponsorship that they just kind of get out there. Same with Visual Basic. A lot of computer scientists hate Visual Basic. They consider it to be, I guess, more like a child's language. Whether or not that's true doesn't matter, but it gets a lot of backing because it's a Microsoft language and it's built into a significant number of their products. So there's one other language that we're going to talk about before we get into the ones that we are going to deal with in this class. And the first one is Smalltalk. And so before we talk about that, we need to talk about another language called Simula. And Simula was developed by Kristen Nygaard and Ole Jan Dahl of the Norwegian Computing Center back in 1961. And Simula 1 was a special purpose version of extension to Algol for programming simulations, right? So think about the airplanes at an airport, customers at a bank, people in a line at a grocery store, etc., right? And then Simula 67, on the other hand, was a general purpose language which had classes, objects, and inheritance, right? And then they also had in coroutines. So they had coroutines rather than methods, right? So it didn't have what we would call all the hallmarks of an object-oriented language, but it had a lot of them. So from Simula, right, came Smalltalk. And so Smalltalk was developed by Alan Kay. We can also thank Alan Kay for a significant number of other things. For example, the mouse. When he was working at the Xerox Palo Alto Research Center, PARC, back in 1972. And this is before he was hired on at Apple and became the guy behind a significant number of products there, along with our good friend Steve Jobs. Anyway, so aside, inspired by Simula, another language, Sketchpad, Logo, and then along with that, cellular biology and probably ontology and like 15 other things. He developed Smalltalk, and Smalltalk is considered to be more object-oriented than most of its popular descendants, so its children, like Java, like C++, mainly because everything in it is an object. So all variables, constants, activation records, whatever you think about, classes, are all objects. And that's what makes it what I would call a more pure object-oriented system. So think about, right, all the computation in Smalltalk is done as objects sending and receiving message. So the message here is we are sending the message to 1 to add the combination of the message that was sent to 2, which is 3 multiplied by 3, right? So we typically think like sending a message is calling a method on an object. So the star here on 2, the 2 times 3 part, is really saying calling the method multiply on 2 by 3, right? The message that we're sending to 2 is the value 3, and through the channel multiply. And we're taking that number, which that returns, right, the 6. And so we're taking that 6 and we're going to add it to 1, leaving us 7. So the design philosophy behind this language, Smalltalk, was to commit to a few simple ideas and then find the most elegant language design from there. So you have and this happens a lot, right? For example, think about Lisp, right? Lisp had lists, recursion, and then they had this really simplistic way of evaluating things called eval, the eval function, right? Smalltalk, objects, message, and message passing. In Prolog, which we'll talk about, they have the basic concept, resolution-based inference. That's it. The hallmarks for good design of languages: initial implementation is easy, it's easy to modify language, and programming feels like custom language design. That's good design in a language, right? And when we talk about Ruby, we'll talk about some of that stuff. Smalltalk's influence was that, the similar language Smalltalk inspired a generation of object-oriented languages. These include Java, C++, Ruby, a whole bunch of different things. Smalltalk is still used today. Smalltalk also is the place where one of the most widely used design patterns ever came from, which is the model view controller. That came from Smalltalk. Most later OO languages concentrate more on, current OO languages concentrate on runtime efficiency. So for example, in Java, C#, these two languages they focus on static typing, right? So we have to state the type of a variable when we use it at the time that we write the code, prior to it being compiled. On the other hand, Smalltalk uses dynamic. Interesting enough, Ruby also uses dynamic typing. So does Python. Most include non-object primitive types. For example, Java's base level types like int, character, Boolean, all those different things. Those are our basic primitive types. They're non-objects. C# in the .NET platform has a bunch of those as well. But if we look at Ruby, Ruby does not. There are no there are no primitive types in Ruby. But Python has primitive types. So now we move on, right? We've gone through a significant number of languages that were developed well before any of us were born. Now we move on to, still languages that were developed before any of us before we were born. But the first one we'll talk about, which is the last language we're actually going to cover in the course, is Prolog. So Prolog was developed, starts from this concept by Alan Robinson back in '65, which was a resolution-based theorem proving. So resolution is a logical a method in first-order logic, which allows us to resolve logical variables, right? And so we'll talk about how that actually works when we get to Prolog. But it's the basic concept underlying Prolog. Unfortunately, though, just because we've come up with a resolution-based theorem prover does not mean we can actually develop Prolog from that. The problem is Robinson's version was not what we would call efficient enough to handle the resolution necessary for Prolog. So that led to Robert Kowalski in Edinburgh back in 1971, developed an efficient resolution-based technique. He called it SL resolution. And then came, Elaine Commerer and Philippe Rousseau in Marseille back in '72. They developed Prolog, right? So over in France, they came up with this method. What it basically does is the whole goal of Prolog was to get into automated deduction part of an AI project, right? For natural language understanding. So this is the interesting thing. This actually sparked a debate. This is an aside. The debate was on what is the language of thought, or what they called LOT. Language of thought, is it symbolism, like symbols, like as in Lisp, or is it logic, as in Prolog? And that led to this debate that kind of sparked what is called the AI, part of the AI winter back in the 80s, but that's an aside. So then this led to the Prolog evolution, right? So in 1973, the version included, basically eliminated special backtracking controls and introduced the cut operation, but it also eliminated what's called the occurs check. And then in '77, David Warren developed an efficient compiled Prolog, and what he called the Warren abstract machine. So it's an underlying, basically virtual machine on which Prolog was going to run. And then for many other languages, Smalltalk, Prolog, ML, the techniques developed for efficient compilation were the critical contributions, right? To make them useful languages for the rest of us. Because back then, processing capability was quite limited compared to what we have today. And then finally, in 95 and 2000, ISO standards for Prolog came about. So then we get to the story of ML, right? So in Edinburgh, in '74, Robert Milner developed a tool called LCF, a tool for developing machine-assisted construction of formal logical proofs. And then ML was the language designed to implement LCF, right? So one of the hallmarks of what's going on in ML is we have strong typing. It's not static typing, but it has strong type inference, right? Parametric polymorphism, and these things were all in the first designs, right? And so then ML became closely tied to the LCF development for several years. Well, then this got into a problem, right? So the issue was formal semantics. So the definition of standard ML includes a formal semantics, a natural semantics, if you will. It was part of the initial design, but not added as is more common after the initial the implementation, right? So the formal semantics are not a part of the actual implementation. So it fits with the intended application. So the basic concept here is, in order to trust the proofs by LCF, you must have trusted the language in which LCF was implemented. And then the evolution of ML, so comes along as this, right? So in '80, Luca Cardelli developed an efficient compiled ML, right? Remember, we talked about the efficient compilation is the key here. And then in '83, a draft of the standard ML was published. So the additions that included were like pattern matching, which we'll talk about, modules, named records, exception handling, streams. And then now we've gotten to this point to where there are a whole bunch of different dialects. So there's the standard ML, which we're going to use in this class. Lazy ML, which uses a lazy evaluation strategy, and which is similar to how Haskell does its evaluation. Then you have CAML, which was an ML dialect diverged from the prior to adding modules, and OCaml, which is a CAML dialect that adds object-oriented constructs. And then finally, we have F#, which is a .NET commercial OCaml. I've actually programmed in that. It's actually a really fun language to work with. And finally, we get to Java, and there will be a separate video for the evolution of Ruby. So Java is an interesting language, to say the least. It's come from a long line, traces back to Algol 60, like so many other ones. But from Algol 60, we get to CPL, which was a language specifically for business processing. And this is interesting. And the reason I'll say that is back when Fortran was big, the other language that was big was COBOL. COBOL was the language for business processing, and which I'm not talking about besides this aside. And so COBOL, you still find COBOL to this day. There's an object-oriented version of COBOL. There was COBOL, then COBOL 2, then OO COBOL, and so a huge amount of code has been written in COBOL, to the point to where it's been around for 30 years. The interesting thing is, some people have said Java is becoming the new COBOL. And so anyway, moving along. So going back to this, so CPL was the language that was larger than Algol 60 and had a bunch of features for data processing. But then they simplified it down to basic CPL. So they got rid of they made it typeless, manipulates untyped machine words, introduced the C family array idea, where you have the A with the brackets and then an I written after it, right? But they called it A. I believe that would be A bang I, or the exclamation point I. Is the same as a reference to the word address, A plus I. Interesting enough, that's how C is actually doing it. So this was created by Martin Richards back in '67. And then this gets us to B, right? B was an even simpler language, right? Designed for systems programming for the first Unix system. Now, I would hope that everyone who's taken C would know all this right now. If you don't, awesome, because now I'm teaching it to you. Otherwise, because the most important thing is B, right? B is what led to C, and we'll see that in a second here. B was developed for systems programming, which led to the first Unix system at Bell Labs. Right, Unix came from Bell Labs. B was actually named, we'll say for Bell in Bell Labs, or at least claimed that way. But and include the first compound assignments like the plus equals, and borrowed from Algol 60 and was created by Ken Thompson in 1969. So that's the interesting thing. Now, that's where C comes in, right? C is an extension of B, and it was originally apparently NB, which may have been for not B, and it was designed to take advantage of more hardware, including the PDP-11. I'm hoping that everyone learned about all these different systems when they took architecture. If not, go read a history book on computer science. It'd be awesome. Or go to the Computing Museum here in Bozeman. So type systems were included, macro preprocessor, an I/O library, etc. As actually C was quite impressive for his day. And then they used C to re-implement the Unix kernel, right? And then it came with Unix. So if you had Unix, you had C. And C was written by Dennis Ritchie back in, it was actually Ritchie, Kernighan, like a whole bunch of other people back in 71, 73. I actually had the original C programming book, the original edition, pristine from on programming C written by Ritchie and Kernighan. Then along came C++, right? Originally it was supposed to be just, a preprocessor that added object-oriented concepts to C, but it ended up becoming its own language in itself, and this was originally written by Bjorn Straussup back in 84, right? So now he's adding in things like overload operators, function names, dynamic dispatch, exception handling, templates, which the C++ template language in itself is Turing complete. But it became one of the, and now it's still C++, C, probably the most widely used languages, I would say, on the planet, maybe next to Java. Every time I look at, there's language indexes, every time I look at those, C, C++, and Java are the top three. So then, C++, right, that's 84, and then James Gosling, a researcher at Sun Microsystems, back in 91, designs a language called Oak, okay? And was designed for small computers, right? Think about where we are today with all these tablets and phones and everything that we have. I mean, toasters have integrate systems that, you can get a smart toaster and all these different things, right? And then you have all the small devices like Raspberry Pi and things like that. That's what James Gosling envisioned Java to be for. Unfortunately, all those things weren't around back in 1991, and so Java was, that concept was a little bit before its time. But there was something else that came about. So anyway, just like C++, he wanted it to be just like C++, but smaller, simpler, right? Get rid of the template language, get rid of all these different things, but he also wanted to ensure that it was more secure, it was strongly typed, and he wanted to be platform independent. So the interesting thing was C, C++ had this really great concept. Man, you write the code once, and then you can compile it on, and then so the code doesn't have to change. So back in the days prior to C, if you wrote code for a program, well, you may have to change depending on the system that you write it for. So the code was a little more connected to the hardware than needed to be. So C said, we're not going to do that. We'll let Unix or the operating system take care of that, the execution part. You write the code. As long as you have something that can compile it down, then you're good. Well, that was great, except for the fact that the write once, compile anywhere was not good enough for Java and for James Gosling. He wanted it to be write once, compile once, run everywhere. And that's where this more platform independent concept came from. And so then, in 1995, they renamed Oak to Java, and they retargeted it for the web, right? Remember, because I told you they wanted this ubiquitous computing concept, but ubiquitous computing didn't exist yet. That didn't happen until mid to early 2000s, right? When everyone started getting smartphones and tablets were everywhere. So that's what we have now. But 20 years ago, they didn't, or almost 30 years ago, they didn't have that. And so back in 95, they renamed Java, and then they targeted it towards the web. So back back then, this is before what they called for a little while Web 2.0. This is before we had everything running JavaScript and all these really great frameworks for both client and server-side processing. And so what we basically had was nothing. And so JavaScript didn't exist exactly at this time. I don't think it came out until 97. And so we needed some way to provide active content for web pages. And so Java filled the bill. And that was what we called applets. Now, if you try to run an applet in a web browser today, you probably won't be able to. Why? Mainly because every web browser on the face of this planet has decided that Java is a little too insecure, and we're not going to do that. But anyway, at the time, that's what we made it for. And it was actually pretty interesting, and you had this new way of doing things. So that's what Java was for. But in reality, Java doesn't have quite the nonlinear lineage that we expect. Java also has concepts like garbage collection and concurrency and packages, all coming from different languages. But the interesting thing, as I said earlier, is that nothing in Java is new. It's intended to be a production language. They wanted this thing to be up and ready and running for the enterprise, or at least for real programming, in the first place. And so it was not designed to be a research language like so many other ones. That being said, if we go and, to conclude all this, there are almost all these major language pioneers that are listed here have won a Turing Award, which I don't know if you know, the Turing Award is essentially the same as, it would be like what I would call the Turing Award is basically like is considered to be like the Nobel Prize for computer science. Anyway, so all these bright people, they worked really hard, and now we grab all these great things that they that seem really easy to us, but weren't back then, including like variables, local variables, block scope, using things other than goto, and hopefully, right, these same perfectly obvious things to everyone were unknown and unguessed back then. The goal would be for them, for us to come up with new things, right? So this is, well, we have the question, are we done? Some people might think that with all this stuff that has happened, with all the languages that we've created, there's not really nothing left for us to do. Well, that's the next question. Maybe all the important discoveries have been made, and language evolution will slow or converge, or will it, potentially, will we find new things that are currently unknown, unguessed, right? And that will eventually become obvious to everyone, but are not at this time. So, I'd like you guys all ponder that and enjoy the rest of this course.